Good morning, everybody. Can you all hear me?
Yep.
Okay, cool. Great. So, welcome to Physics 210. We're going to meet every Tuesday for a lecture. I know it's a 3-hour lecture. I think what we're going to do, what I'm going to do, because I need a break too between in this lecture. I will probably lecture until 12:25, 12:20, 12:25. We'll take about a 20 to 25 minute break, maybe eat lunch or something, and then we'll continue again. How does that sound?
Sounds good.
Okay. Just a second here. So these lectures are recorded. Now I record them on Zoom, but I also record them on my video capture software. And the reason why I do that is because sometimes I have internet problems, the internet's unstable, and so when that happens, the video will look bad on Zoom. So I have my, I'm actually recording right now, and of course I have to remember every time to start my video capture software when I start the lecture. So when I record the lectures on my video capture software, I then upload them onto my YouTube channel. Okay, so I actually have a YouTube channel called DC Physics, Rockland, California. And there will be a playlist for our lectures. Okay, so there will be there too. And in fact, if you go there right now, you'll actually see all the lectures that I've posted the last 3 semesters. Okay. So if you miss anything, you can actually go to this channel and find. Uh-oh.
Recording in progress.
Okay, sorry, I guess I disappeared there for a minute. Anyway. Yeah, I apologize. My internet connectivity got cut off. Okay. So, yeah, unfortunately, there's 2 of us in this house using the internet to do Zoom meetings. Okay. You can't hear me? Oh.
Professor, you're muted.
Okay, thank you. All right, what I was saying is, unfortunately, there's 2 of us in this house using a Zoom to do meetings. So sometimes I have problem with connectivity. I think what's going to happen later on in the semester, I'm going to try to do my lectures on campus, so that this issue won't be as big a deal. Okay, but right now I'm lecturing from home. Part of it because I don't have any demos in the first unit. So what I was saying is, my lectures are also on this YouTube channel. So you can go to the YouTube channel and watch the videos. So now the issue that we just had, you'll see it on the Zoom video, but you will not see it on the video I'm recording separately. Okay, because my software is capturing whatever I'm doing here, whereas the Zoom is capturing what's happening with our network too. Okay. All right. So if you miss a lecture, go ahead and watch it on YouTube or on ConferZoom. So the first thing I want to do today is really answer your questions you may have had on the introductory video. What questions do you have?
I saw one of the things we have to do this week. Might be mixing up my classes, but we have to do Webassign, which is on Canvas, right?
Yeah, you'll access Webassign through Canvas now.
Okay, and then we also had to submit something like a signature.
Oh, okay. I'll bring. Let me talk about that. So, the last page. So I expect you to read your syllabus. Actually, I expected that you have read your syllabus already. And although I think I might have sent you the wrong version, I might have sent you the Monday, Wednesday version. So I emailed you just before class the Tuesday version, sorry. And so the only difference is the scheduling. If you read the last page of the syllabus, there's an affidavit. Okay? So what I want you to do is sign and date the last page of the syllabus saying that you've read it and you understand the terms, and then upload it into the assignment for the affidavit. If you look at the first module, there's a place where you can upload it. And when you do that by Saturday, okay, and I think I have to fix the due date on Canvas, I will add half a percent to your grade at the end of the semester. It will not show up on Canvas, but you know, when I look at your grades, I look at your value and then I add 0.5% to that. Does that make sense?
Recording in progress.
Okay, I'm sorry. I don't know how much of that you missed. Did you catch some of that? Did you catch any of that?
I thought you might have sent us the wrong one. Something about.
I'm sorry, I didn't hear you.
I just heard something about Monday and Wednesday possibly being the wrong syllabus.
Yeah, so I emailed you the syllabus just before class, just in case.
Okay, all right.
Okay. The only difference is the schedule. But then
Right.
sign the last page and turn it in via Canvas. And I give you half a
So
credit, half a percent credit. I'm sorry.
Okay. Oh no, it's okay. So for the signing, we sign it like physically, and then we scan it onto Canvas, essentially.
Yes.
Okay. All right.
Yeah. Okay. Other questions? By the way, I apologize. I've never had it this bad where at the beginning of the class, the Zoom went down twice. That's never happened to me. Other questions? Or concerns regarding the course? Okay, so let me say a few things then. So I'm going to be saying a few things regarding the course today. We're going to cover the course in a different way. We're going to start on chapter 39. So I know this course is on electricity and magnetism. But what I want to do first is talk about relativity, because usually that's at the end of the semester and I usually have very little time to cover it. And because we're online and I'm having the exams in person, I have a little bit more time to cover this material. So I'm going to start with chapter 39 this semester. Okay. It's an interesting topic. You'll probably never see it again after you're done with this course. It might make you uncomfortable at first because it's weird. But you'll get used to it after about the second lecture. Okay, once you've done the homework, you'll feel a bit more comfortable with it. Since this only covers one chapter, this first unit, your exam is worth less. So I'm giving 5 exams this semester. The first exam is worth 9% of your grade. The next 4 are worth 18% of your grade each. Okay? I will drop one of the first 4 exam grades. I will not I will not drop the 5th exam grade because I'm not giving you a final. But you need to be able to go through the last unit because some of you folks are going to be taking Engineering 17. And if I drop any one of those exams and you decide, oh, I don't want to do Unit 5, then when you get to Engineering 17, you're in trouble. Okay? So that's why I do it this way. So I will drop one of the first 4 exam grades. And the reason why I do that is because I don't give makeup exams. Okay, that's the reason why. But then I make it fair to everybody. I just dropped the lowest exam. At least it makes a big difference for you guys. Any questions on that? Can you still hear me?
Yep.
Okay. All right. I need you to get to Webassign as soon as you can. I'm not sure how you access Webassign last semester, if you accessed it through Canvas. Did you access Webassign through Canvas last semester? Okay, if you did, then it's the same way this semester. So what you have to do is look at the modules, and the assignment will be in the module, and you click on it, and you get to your homework. So this first unit only has one homework assignment. It'll be on chapter 39. It should be available to you. I was having some issues yesterday, so if you're not able to access it, please let me know. Please let me know if you have any issues. Okay? If you do, probably have to contact Webassign. Webassign has changed over the years. It used to be run by a university, and we got responses really quick on problems, but now it's run by Cengage. Cengage bought them out. So things are somewhat slower with them. Okay. Now, before I forget, on every Webassign, there's you can't get an extension. There's a button that says extension. It'll automatically grant you an extension for a week once the deadline is passed. But then there's a penalty of 50% of the points you haven't earned yet. So if you've gotten, my homework assignments are with 20 points. So if you've gotten 14 out of 20 points on the homework, that last 7 points, if you want an extension, will be worth half that, 3.5. So the highest you can get is like 17.5 points, which is still 85%. Make sense?
Yes.
Yeah.
In the syllabus, I mentioned that I do homework assignments, the Webassign, plus worksheets. I used to have the worksheets, have the students do the worksheets, write on them, and then upload them onto Canvas. And I'm notoriously slow at grading things on the computer. I'm just a bad typist. So what I did was I took those worksheets and converted them into a Webassign. I had the code over the summer. I wrote some code to make the assignments onto Webassign. So all the worksheets will be on Webassign. So pretty much every assignment that you do in this class, at least in the lecture part of the course, will be done on Webassign. The exams are the only thing where you're going to handwrite a solution to it. Okay? Now during office hours, during my student help hours, which are on Thursday, 5 to 6:30, when we talk about a problem, it would be nice if you show on the screen how you did the problem. That way I can help, I can help you, guide you through it. Okay. The stuff underneath regarding the exam in this slide, I forgot to change. I'm going to have to update that because our exams will be in person during lab. So that's a mistake. I have to fix that. Okay. So another thing that I've changed over the last semester was my grading policy. Because I'm giving the exams in person and the dates are given, the first test is September 10th, I can give you more traditional type problems. So students are able to do generally, historically better than on the online exams. In the online exams, I actually have to give non-standard problems. So the previous 2 semesters, I was making up non-standard problems. And of course, exam grades tend to be lower in those cases. So I actually had to grade on a bell-shaped curve. Okay? I had exam scores last year like 48%, 54%. They were pretty low because I had to give non-standard exams because if it's easy to Google standardized problems. Okay, I'll be honest. That's the case. So I gave a lot of non-standard problems. So, but if we're going to be doing the exams in person, I'll give you standard problems, and the exam shouldn't be too bad. Okay, now the exams I put on Canvas right now or the sample exams that are on Canvas right now are based on the online exams I gave last year. As we get closer to exam time, I will email you sample exams that are the type you would encounter in class. Okay?
For the lab, I saw that it's like 2 weeks in person and 2 weeks online. When it's online, will we have like Zoom on those days?
When it's online, we'll have Zoom. In fact, we'll,
Okay.
when it's online, we'll have Zoom. From October 29th all the way to the end of the semester, everything's in person. Whether it's an exam or not. And part of it, the last couple of labs were very problematic in 210 because the equipment that I had to use was bad. Okay? It was problematic to the students in collecting decent data. You kind of had to be an expert in how to figure out how to make it work right. So this semester, we're going to be doing those last couple labs in person. It makes it a lot easier. Okay. By the way, the days I have exams, I also have something called open lab. So you are going to be doing take-home labs, but those times where I have open lab, you can come bring your lab to me and I can help you with it. It's way easier than answering your questions via email. Okay, so on the Fridays where I have exams, I also have something called open lab, either before or after the exam. And I can answer your questions regarding the lab. So bring your equipment. So come early and come before the exam, bring your lab questions on those Fridays and I can help you. Okay? Because the campus will be open. Okay. I encourage you folks to, if you have questions on anything in the course, on course material, to use the discussion board or Discord. One of the students in the other section created a Discord for us. And so I invite you to join it. I have the link on Canvas. And so I actually always have it on. So if I'm in front of the computer, I see a question pop up, I'll answer it. All right. And you can ask each other questions regarding the labs. You can ask each other questions about the homework. Over the past year, it has been very useful. If you email me questions, my guess is a lot of you have similar questions. It's very inefficient for me to just spend time emailing students individually. However, if I see the question in the discussion board or on Discord, then the questions can be answered more efficiently. I can answer them, another student can answer them. Or both of us can provide an answer, and maybe one of our answers might make the light go on for you. Okay? Okay, next thing is the lab kits. Have you picked up a lab kit yet?
Not yet.
Not yet? Okay. So the lab kits are being handed out today and tomorrow from 8 to 4. Okay? Need you to pick up the lab kits. One of the issues, and not really in 210, there's a reason for it, but in some of the other courses, students wouldn't even pick up the lab kits. So I don't know what happened with their labs. But in my course, probably not, because several of the labs you're going to do this semester, you have to videotape yourself doing the lab. Your report is a video. Okay? So I'm pretty sure most of my students use their lab equipment. Okay, so I need to use lab equipment, the lab kit. If you don't pick up the lab kit, that shows me that you're not interested in the course, and I'll drop you. So you need to pick up the lab kit. Okay? Now, there's one piece missing in the lab kit. It's a big multimeter that just came in late. That's coming in late. And so we'll give you that second one when you have your first exam. Otherwise, please pick up your lab. You're gonna need the lab kit starting next week. Okay? So please pick it up as soon as you can. If you're having an issue trying getting the lab kit today or tomorrow, please let me know. Please email me. Okay? Questions on the lab kits? Of course, we need them back when you're done with them.
And they're in Sewell Hall, right?
Yeah, they're in Sewell Hall. As you walk into Sewell Hall, there will be somebody at a table greeting you, and they will just. What will happen is they'll ask for your name. They'll write, they'll put they'll write your name on the list, and then they're going to have you write your name on the box. Okay, and then that's it. The boxes are about so big. Oops. The boxes are about so big. They're not big boxes because the main equipment, the big parts we're going to be using in person at the end of the semester. Okay.
Okay, thanks.
Other questions? Or concerns? Usually I spend more time talking about the class, but I figure with the introductory video and everything that's on Canvas, I don't need to spend as much time on things. Last week, as I was starting to prepare for this class, I started reading this book, and I don't encourage you to read the whole book, called Basic Relativity. And the author is named Richard Mould. And there's one chapter on it that would be particularly good for us. If you read it carefully, I think it'll help you a lot in understanding the material. The book is actually, you can actually find it on Google Books. If you type Richard Mould, Basic Relativity on Google Books, you'll find it. And you only need to look at chapter 2, which is about 15 pages, I think. Okay, all the basic principles of relativity are discussed that. The physical reasoning for some of the equations will be here. Okay? So I list some of this stuff out so you can, the YouTube channel. Some people subscribe to it. I'm not here to make money, so if you want to subscribe to the channel, that's fine. If you don't, that's fine. It's fine. It's not a big deal to me. This is just a placeholder for the videos. Okay, and I had to make the YouTube channel public so that I don't have to give you a private. I don't have to email you the link every single time. Okay. All right. Any other questions, concerns? Oh, good question regarding the exams. Are you allowed to bring your own equation sheets? I will give you, so the first page of the exam will have the equations on them. Okay? I will put on the exam the equation like conservation of energy, conservation of momentum. Those will be on there. Okay? So I'll give you that. But I don't have you. But you don't bring your own exam, your own sheet. In fact, when you come to the exam, all you need is something to write with. Because I even have the calculators. The calculators have to be scientific calculators, no graphing calculators or anything like that. Because I might have you make a graph on the exam. Okay.
Are we meeting up this Friday? I'm actually confused, like, because you said about like the exams and the labs and stuff.
I'm sorry, I didn't catch your question.
Are we gonna be meeting up this Friday then?
Oh, online. We're meeting online Friday.
Okay, so not on campus.
Yeah.
Got it.
There's only 8 days that we meet on campus. The first one is September 10th. Okay. The second one, so our meeting, our days on campus are going to be September 10th, October 8th. I can't remember all the other ones now.
Oh yeah, I remember the chart, the syllabus actually.
Okay.
You had it on your syllabus, all those dates.
It's just the exam days?
Well, 5 of them are exam days, 3 of them are for a lab.
Okay.
Okay. But remember, on those exam days, I also hold open lab. So you can bring your lab with you and ask me questions. So on Canvas, I've written down what my open lab times are on those days. And so you can come before or after your exam. You can come to any of the open lab times, by the way, you can come to any of the open lab times to ask your lab questions. But your exams will be at 2 o'clock, right? Your exam will be at 2 o'clock on the Friday. And then afterwards, I will have open lab, and now I have actually open lab before that too. Okay. It's way better to answer your lab questions in person than online. It's really hard.
So is Open Lab, sorry, I probably said, Open Lab is every Friday or just test days?
Just those, just
those in-person days?
Yeah, just the in-person days.
Okay.
Okay. However, I plan to be on campus Mondays. So I teach a class from 9:30 to 10:50 on Monday, which is 2:10. Okay. Then I will try to hurry and get to campus. I have meetings at 3:30 on Mondays. So in the time between maybe let's say 11:30 and 3:30, I'll be on campus to answer questions. So I'll be there. Or I should say I'll try to be there. If you're going to be there, let me know. Okay? Let me know if you need to come on Monday, ask a question on anything. Just let me know. Okay? My goal is to be there. I didn't schedule in the syllabus or anything because something might come up where I can't go. And so but my goal is to be there on Mondays. Now, our instructional assistant will be there on Mondays. So you can probably go there on Mondays and ask our instructional assistant questions on the lab. Okay. So this semester is going to be a little bit different because there's going to be a little bit more availability of us on campus to you guys. By the way, I don't know if you heard, you don't need a parking pass this year, at least this semester. You can just go in and park anywhere. Other questions? Yeah, you can. I think you can park in the S lot. Because they're not checking parking stickers. I think you can park in the S lot. I mean, you can double check on that, but you know, you don't need a parking pass. I mean, I don't know if they can tell the difference between a student and faculty if there's no parking pass. Because I don't have a parking pass. In fact, my parking pass that's on my car expired last year. So I don't think they're going to be handing out tickets this year.
I tried to even just get one and it said that like there didn't even open an ability, like any page to even buy one. So I don't think they're available at all.
Yeah. Anything else? Okay. I was worried on the first day. There's so much information on the first day, but a lot of it's on Canvas. regarding the course. So what I'm going to do then is I'm going to start on chapter 39. So let me switch my PowerPoint slides. And I'm going to send you guys a corrected version of this introductory one because I noticed a couple of mistakes. Okay, so chapter 39 is on relativity. So, I'm doing something unusual. I'm going to use the beginning of the semester. The first 2 lectures will be on relativity, and then you'll have an exam on it the following week. Okay. One of the disadvantages of the one day a week classes is how things are spread out. It's kind of strange. Okay. Oh, a question regarding, I'm sorry, I missed the question regarding the parking garage. The parking garage is open. Okay, our parking garage is actually open right now. So yeah, go ahead and use it. It's huge. Okay, the parking garage is twice as large as any building on campus. Okay, so let me, so relativity is going to make you feel uncomfortable. It defies common sense. It works though. Okay? And so you'll feel uncomfortable with it at first. You'll feel uncomfortable solving the problems. But I think as you do a few more, it'll get better. In fact, I personally think the material at the end of the unit on energy and momentum is easier to work with than the stuff I'm going to talk about today and next week, the beginning stuff. Okay? That's how I feel. I mean, that's my viewpoint. So you will feel uncomfortable because it's bizarre. But you'll get it, I think, after you work on the homework problems. Okay? So make sure you read chapter 39. If you have the opportunity, you should try to look at this book. But I would look at this after you've read chapter 39. Okay? I do expect you to read the chapter. So don't read the whole chapter 39 at once. Oh, regarding the garage, I haven't tried to access the garage yet, but I mean, I know you have to access it from Sierra College Boulevard. I think that's the only way to access it. Okay.
Are we able to start the homework after today's lecture, or do we have to wait till we're done with chapter 39?
I'm sorry, I couldn't hear your question.
Are we able to start the homework today after the lecture, or do we have to wait till the end of the section?
There might be, yeah, I don't know. I mean, there might be 1 or 2 problems you can do.
Okay.
I'm hoping you can do a couple of them. And I think after next week for sure. Yeah, again, the problem is with the 1 day a week lecture. It's kind of hard. You have to wait longer. But
yeah.
You might be able to do 1 or 2. There's like 15 problems total. Maybe you can do 3 of them. 3 basic ones. And then you could probably do a lot more next week. Okay. All right, so what I want to do is I want to focus on first the issues that led to the development of relativity, and then talk about Einstein postulates, and then the consequences. That's my goal for today, is to talk about the postulates and really the consequences of those postulates. All right? Just a second. So I want to go back to something you learn in 205, but you might not remember it because we really don't emphasize it too much. And it has to do with this thing called the Galilean Transformation. You know what it is, but you never really probably thought about it too much. So I want to do a little bit of review of some basic mechanics. You might say, well, why are we doing basic mechanics? Because this idea has implications in the material we cover in 210. And it's very basic stuff, but it's not easy, actually. So let's suppose we are on a bus, a school bus, okay? Let me draw the school bus. I'm not an artist, okay? That's our school bus. And I'm going to assign a coordinate system that's attached to the school bus. So this is the x prime direction, that's the y prime. Anytime we are observing at a frame that's moving relative to us, we're going to denote it in terms of the prime, x prime and y prime, okay? Anytime something is moving relative to us, to an observer, it's the prime frame. And this bus doesn't have any wheels. Okay. And the bus is moving to the right. And you know, the bus is moving to the right. I mean, I can make it move in any direction, but I'm trying to make the argument simple, okay? We can make the bus go that way if we wanted to, but let's make the argument simple. And let's say we're standing on the bus. So one of us is standing on the bus, at the back of the bus. Let's say the bus is going at 30 miles per hour. And one of us throws a ball with velocity u prime, or speed u prime, in the forward direction. Okay? And at this instant of time, the distance the ball is from the back of the bus is x prime. So the ball at this instant in time has coordinates x prime and velocity u prime. Okay, so far? Now let's say we have a second observer, somebody else, maybe a physics 205 student, who was stationary, who was not on the bus when you threw the ball. Okay? And this coordinate system is fixed with that person who's not on the bus. And we're going to use x and y with no primes on them to denote how this person measures the location of this ball. So to that person, the ball location is x. Okay? That person would measure this value for x. And then that person would also measure a different value for the velocity. That person is not going to measure u prime for the velocity, he'll measure something else. And I think you can figure out what that is. Let's, for simplicity, let's say that one of you threw the ball at 20 miles per hour. And you can kind of figure out how fast this person is going to measure, what speed that person is going to measure. What do you think that person is going to measure for the speed of that ball? What do you think? If the bus is moving to the right at 30 miles per hour, and a person on the bus, one of you guys, throws the ball at 20 miles per hour relative to you, how fast is the ball is going to be going relative to that person?
Isn't it 20 miles per hour?
It's 50, okay? Yeah, you're right. I mean, we know that from common experience, and that has to do with something called a Galilean transformation, okay? But we're going to derive that equation for the velocity. So let's say that after a time t has elapsed, the bus is a distance v times t from this observer, the Physics 205 student. If I wanted to write x prime in terms of what this person measures, isn't it true that x prime is this distance minus that distance? And isn't it true that this person can write this coordinate as this plus this? Do those make sense?
Yeah.
Okay, and that's the Galilean transformation. And that's the transformation we use when we study Physics 205. Right? And what does that allow us to figure out? Well, if we know this equation, let's calculate the velocity. The velocity dx prime over dt, which is our u prime, which is dx over dt minus the derivative of this respect to time, which is v. This is the velocity of the ball relative to the Physics 205 student. We'll call it u. In fact, if I use this equation to differentiate, I'm going to get a very similar result. So 30 plus 20 is 50, you guys said, right? Does that make sense?
Yeah.
Okay, so I mean, it's pretty obvious. This is the Galilean transformation. It tells you how our measurements, what we measure, how they're related to each other when one reference frame is moving. Now, I'm going to say that the bus is moving at a constant speed the whole time. Okay? Let's assume that the bus is moving at a constant speed. Let's take it one step further and take the derivative of the speed of the velocity with respect to time. And what's that going to give us? Well, it'll give us the acceleration. So I want du prime dt. Well, du prime dt is the acceleration. Du dt is the acceleration. And this is 0 because the bus is going at a constant speed. So what that says is, if the ball were accelerating on this bus, that both people would measure the same acceleration. So that means that F net equals MA prime equals MA. You get the same value in both reference frame. Okay, as long as the bus is not accelerating, that same force gives you the same acceleration in both frames. And that's what you learn in Physics 205 about Newton's second law, right? That frame that's not accelerating, what is it called? It's given a special name. Do you remember what it's called?
Inertial frame of reference.
It's an inertial frame of reference. So Newton's second law is valid in an inertial frame of reference. Now, what if the bus was accelerating? If the bus was accelerating, then these two would not be the same. And that means then for the same force, you'd have two different accelerations. This wouldn't be valid anymore. Newton's second law would not be valid. Okay? You okay with that so far?
Yeah.
And by the way, if you're on a bus that's moving at a constant speed, if you drop the ball, you can't do an experiment which tells which reference frame is moving or not. One's moving relative to the other. There's no absolute reference frame. Okay? So here's the thing regarding the Galilean transformation and when you're dealing with an inertial frame. So I should say that when we do relativity in this chapter and in this course, we're really talking about what happens between two different reference frames. The reference frame is always going to be inertial. That's called special relativity. That was the first, and that was what Einstein came up with first. It came up with special relativity. The reference frame is not accelerating. Later on, around 1913, 1914, he came up with the theory of general relativity, where you're dealing with accelerating frames. We're not going to cover that. That's very difficult to cover mathematically. Okay? So we're assuming here all reference frames are inertial. We're doing special relativity. So the net force on the system has the same value in all frames. That means that this guy doesn't vary in any frame. So we say that it's invariant. Newton's second law is invariant. Because F net is the same value, the same number, no matter what reference frame you're in. Like the distance between 2 points has the same value no matter what reference frame you're in. Okay? And we say that value is invariant. However, Newton's second law also looks exactly the same in two different reference frames. We say that's covariant. In fact, all the laws of mechanics have the same form in all reference frames. All the laws of mechanics. For example, conservation of momentum. Remember what conservation of momentum is? Conservation of momentum says that if two objects collide, oops. And you remember this equation from Physics 205, right? No matter what reference frame you're in, this is the same equation. It had the same form. But what's different if you're in different reference frames? The V's are different in different reference frames. So even though conservation of energy has total initial momentum equals total final momentum, the values of the momentum will be different. And so we say that conservation of momentum is covariant. It has the same form in every reference frame. The equation doesn't change. There's no other terms if you change reference frames. Okay? And you can prove that if you wanted to. Conservation of energy, same thing. Right? Conservation of energy will look the same. Total initial energy equals total final energy. Doesn't matter what reference frame you're in, that's the same idea. You don't have to change terms to it. You don't have to add any terms to it. It looks the same. All the laws of physics have the same form in all reference frames. All the laws of mechanics are covariant. And this is called the principle of Newtonian relativity. So all the mechanics rules have the same form in all reference frames. Inertial, I should say inertial. Okay, and this is the principle of Newtonian relativity. But what happens with electricity and magnetism? Okay, what happens with electricity and magnetism? Turns out there's a problem. Okay? If you apply this transformation to the laws involving electricity and magnetism, there's a problem. And that's what concerned Einstein. Okay? And that's what we want to work on, we want to look at. By the way, if all the laws of physics are the same in all reference frames, if you measure the period of a pendulum in two different inertial frames, you get the same period. That's actually what you would measure. Okay, so question is, how does the Galilean transformation work with Maxwell's equations? So I got to tell you what Maxwell's equations, what Maxwell's equations mean, what that phrase Maxwell's equations. Because we haven't talked about it. You don't need to know exactly what they are. You just need to know what they're for. Our goal this semester is to come up with these four equations. There's four equations. And there are four equations that summarize this course. You can actually reduce this course into four equations, pretty much. You need another one for the forces, but pretty much everything in this course can be reduced to four equations. And they're not easy equations, so that's why we have to spend the whole semester deriving them, at least at the introductory level. Okay? If you apply this transformation to the equations that govern electricity and magnetism, they look different. They have a completely different form and different reference frame, so something's not right. Okay, why should they be different? When in mechanics, that's not the case. Okay, I'm not going to give you an example since we haven't covered E&M yet. What does this mean, though, if this transformation, really basic thing, works for mechanics, but it doesn't work for E&M? What could this possibly mean? Well, it could mean that Newton's relativity doesn't work for E&M, electricity and magnetism. It doesn't work for the stuff in this course. Okay? E&M is only valid at some sort of special reference frame. Maybe it means that the equations governing E&M are not correct, but this thing is valid. Or it means that these equations are correct, but there's something wrong with this. It's either completely incorrect. Well, it can't be completely incorrect because it works for mechanics. But maybe it's approximately correct. Maybe this has to be modified some. And the question is, what did Einstein look at? What did Einstein try? Well, I need to say a few things. So, regarding the special reference frame, I want to say a thing to about A. Because at the time, in the 1800s, after Maxwell's equations were developed, there was this idea that E and M was valid in a special reference frame. And there's a lot of research that took place into this topic. Because I don't have the time to go through all the research. I'm summarizing things. There's a lot of interesting stuff that came up that one can talk about. But, you know, you have to read stuff on your own to really see it, because it's just, there's too much information. You cannot cover it in this class. At the time of Maxwell, when the equations came up, physicists were very mechanistic in terms of describing nature. Maxwell's equations tell you that light travels in the form of waves. And these waves can travel in a vacuum. But if you have a very mechanistic mindset, meaning that, you know, there's got to be something mechanical that's causing these waves to travel, then you would say that electromagnetic waves, you know, the light that comes to us, requires a medium. And the reason why, if you take 215, you'll learn in physics 215 that if you look at sound waves, in order for sound waves to travel through space, sound waves need a medium. What I mean by that is you need one medium to affect another part of the medium. You need one atom to affect another part of the atom. You know, kind of like how when you watch a wheat field, the wind blows across the wheat field. Okay? And you see the wave traveling across it. Or like you see maybe a wave on a slinky. One part of the slinky affects the other part of the slinky. And so the physicists felt light needs a medium because you need one part of the medium to affect the other part of the medium for the wave to travel through it. But here's the thing. The speed of sound, for example, is about 300 meters per second, ballpark. That's approximate. Speed of light is 1,000,000 times that. The speed of sound depends on how stiff the medium is. The stiffer the medium, the faster the sound wave travels. So if we have a medium in which light travels through, it must be pretty darn stiff. And if the light travels through a vacuum, that medium must not have any mass. And so scientists came up with the idea of this thing called the ether. It has no mass and it's extremely stiff. Okay? And they said that the speed of light is measured with respect to the ether. And so they said, well, then that would mean that the speed of light depends on reference frame. And so an experiment was devised. Michelson and Morley devised an experiment to measure the speed of light with respect, let me rephrase that. They devised an experiment to show that the speed of light depends on the reference frame. Okay, and I don't have time to go through the details of the Michelson and Morley experiment. It was an optics experiment that you would probably, you might cover it in 215, depending on the amount of time the instructor has. But this device was so sensitive that if there was a dependence of the speed of light on reference frame, this device would measure it. And guess what? They had no result. It's called a null result. It's one of the few times where not getting a result is important. Okay. They were not able to measure the fact that the speed of light depends on reference frame. that kind of threw out the idea of the ether. I mean, Michelson and Morley's goal was to actually verify, that this idea of the ether, and it didn't. So along comes Einstein. Now, there's debate as to whether Einstein's ideas were based on this experiment, the results of this experiment. So there is debate about that. So I couldn't tell you for sure if what he came up with was based on the results. This was a Nobel Prize winning experiment. So Einstein came up with two postulates. And you all know what a postulate is, right? Something you really can't prove. Right? For example, there's one in geometry. One in geometry is, I forgot what it's called, because I haven't had geometry in years. But if you have a line and a point above the line, or below the line, doesn't matter. There's only one line that passes through that point and is parallel to the bottom line. That's a theorem, that's a postulate in geometry. You can't prove it, but you know it's true. Okay? So Einstein came up with these two postulates. So what's the first postulate? Well, until Einstein, all the laws of physics were the same in mechanics. Einstein said all the laws of physics are the same in all inertial frames, whether you're talking about electricity and magnetism, mechanics, whatever. See, the ether theory assumed that all the laws of physics were, well, the ether theory assumed that there's an absolute reference frame, which would be the ethers. Okay. Einstein said there is no absolute reference frame. All the laws of physics are the same in all reference frames. No matter whether you're talking about mechanics, E&M, thermodynamics, doesn't matter. Okay? So that was the first thing he said. And the second thing he said, which was more daunting, was this. That the speed of light has the same value regardless of what reference frame you're in. Now that was a hard pill to swallow. We have yet to prove that, because it's pretty hard to launch a light source at high enough speeds for us to prove it. Okay? But the theory does work. So what does that mean? If you're on a bus, let's say you're on a really fast bus that's moving at half the speed of light in that direction, and you shine a flashlight in that direction, and I stand here and I measure the speed that light's coming towards me, guess what the value is? It's still 3 times 10 to the 8th meters per second. That's what that means. Okay. So Einstein used those two postulates. Remember the Galileo Transformation? Einstein used the postulates then to derive a new set of transformations. I should say application of Einstein's postulates gave us a new set of transformation. They're called the Lorentz transformations. And I'm not going to derive them. I'm just going to state them later on, probably next week. But it turns out that if you're moving real slow compared to the speed of light, and you approximate the transformation, you get those equations. So these are still valid if objects are moving slowly. These are easy to find to use if the objects are moving very slow, compared to the speed of light. And of course, when you study mechanics, things are moving slowly. So there's no way we can see if there was something wrong with these. Okay, but the Lorentz transformations are really what are the correct transfer, at least based on our knowledge today. That's the most correct transformation that we know of for objects moving at a constant speed. Okay, and I'll show you them later. But what happens is in the limit, I shouldn't say no limit. When V over C is much, much less than 1, then these work okay. Okay. In the limit when V is less than C, these work okay. So that's fine. So I'll talk about the Lorentz transformations later. I want to talk about the implications of those two postulates. Okay, that's my goal today. By the way, before I start that, you can derive the Lorentz transformations with Einstein's second postulate. In fact, when the Lorentz transformation was derived, people were starting to think about, the basics of physics. And there have been people who were able to derive the Lorentz transformation just using the first postulate. The only problem is that you get this thing called a limiting speed and you don't know what it is. Okay, Einstein kind of shows you that the limiting speed of anything is the speed of light. If you ignore the second postulate and you use the first postulate to derive this, you don't know what the limiting speed is. It's something, but what is it attributed to? Okay. All right. It turns out that Einstein's postulates mean that time interval measurements depend on reference frames. In other words, clocks do not run at the same rate in different reference frames. Let me grab another marker. So I'm going to talk about one of the implications of this. So this is a little bit mind-blowing, I think, the first time you see it. So let's do a little thought experiment. And let's say we are watching somebody on a rocket. So a rocket goes by us. Somebody's on a rocket. And the person in the rocket is doing a little science experiment. Person on the rocket shines a beam of light to a mirror, and then the light comes back. The distance from the person to the mirror we'll call D. Since the rocket is moving relative to us, we're going to say that that's the prime frame. Okay? We'll call it the prime frame. Are you able to see that okay?
Yeah.
Okay. I just want to make sure, because when I look at my camera, it looks kind of hard to see, although what I'm looking at is real small. All right, so that person then that goes by us measures the time interval between when the light's emitted and then the light comes back, they measure time delta t prime equals 2d over c. So does that make sense? So if that person had a clock, they would measure this time for the light beam to go up and back down. Does that make sense? Right, that's pretty, I mean, that should be pretty straightforward. What gets bizarre is when we look at it from our frame, the rocket goes by us as the person's doing that experiment. So that's what the person would measure. What would we measure? I want to use the word measure. I don't want to use the word appear or anything like that. I want to talk about what we would measure. Okay? So let me draw what would happen, well, what we would observe and measure in our frame as the rocket goes by us. So first, let me drop up here. I'm going to draw it in 3 steps. Okay, there's the mirror. There's the person. And the light beam is sent upward, but to us, the light beam is going to go like this because the rocket's moving to the right. So when the rocket gets over here, when the rocket hits the mirror, when the light beam hits the mirror, we will observe this. Right? And then when the beam returns, we will observe the beam do this. Does that make sense? That's what we would see. Now, the speed of light is going to be the same. We're going to assume, again, Einstein's second postulate, the speed of light is the same in the raw reference frame. So the light travels this distance at the speed of light. In some time t, whatever that time is, okay? My goal is to compare the time I would measure to the time that person would measure. So the distance traveled by the light, let me use blue. But that distance is also, let's use the Pythagorean theorem. That distance is this square, which is going to be the rocket speed over 2. That's d. The total distance traveled, okay, so the total distance traveled by the light is this. The total distance traveled by the light from here to here is just c times half this time. Okay. This distance then, I use the Pythagorean theorem. I'm going to call it delta t, by the way, sorry. Because I'm measuring a time interval, I'm not measuring an instant of time. Okay. And this distance is that makes sense? What must be true is that this number has to be equal to the sum of these two. And I want to solve for delta t. Let's square both sides. Okay. Let me move this to the other side of the equation. By the way, this 2 squared cancels with this guy. I can pull out the delta t. And so I get delta t squared is equal to 4d squared over c squared minus v squared. Let me take the square root of both sides. So I get delta t equals next thing is, let me pull out from the denominator, I'm going to pull out a c squared. So I get this. Let me know if you can't see something. Now, what do you say about this time? Now, this 2d over c is this term. So, in fact, I can write it like this. Delta t times gamma. Gamma is 1 over 1 minus v squared over c squared. So let me write what gamma is. Greek letter gamma. How big is that number? Is it bigger than 1 or less than 1? Oh, it's behind the slide, sorry. That better? Okay. So is this bigger than 1 or less than 1? Well, v can't be bigger than c because otherwise I take the square root of a negative number. V has to be less than c. This denominator is less than 1. 1 over a number that's less than 1 is bigger than 1. So gamma is greater than or equal to 1. So that means that if that person measures this time, we're going to measure a bigger time. It means that that person's clock is slower. Moving clocks run slow. That's completely contrary to what you're used to. The clocks run at the same speed no matter what reference frame you're in. That's not true. In reality, moving clocks run slower than your clocks. And that has important implications. And I'm going to show you some examples of where this actually works. We're not talking about just clocks. I'm talking about biological systems, any system. Something that decays radioactively. The clocks will run slower if they're in a moving frame compared to us. It's real. It's not an appearance. It's something you would actually measure. You can measure these things in the lab. Questions on this?
I'm confused on where you got delta t equals delta t gamma.
Oh, you know why? Because I don't know if that helped. So when you look at this equation, isn't 2d over c delta t prime?
Yeah.
Okay, so all I did is substituted the delta t prime here. Does that make sense?
Yeah.
Oh, a little bit.
Right, I mean, I just made a substitution, right? I mean, all I'm saying is this is delta t prime. Right, this is the same as that. That's what that equation shows. That's what I derived. You're not comfortable with saying that. With me saying that. Why is that? All right, I mean, you don't seem comfortable for me putting this as delta t prime, which it is, because that's what I said what it was here. I mean, I guess the question is, what is the objection to it?
So when you started the problem, you just wrote that that's what delta t prime equals?
Yeah, that's what that person measures,
Okay.
right? That person measures this. And so I'm writing it in terms of what that person measures. And then, of course, this is gamma. Okay?
But like, how did you get that right equation? Like the delta t equals delta t prime gamma.
This one? Well, I defined this to be gamma.
Okay, I got that.
Okay. And then this is delta t prime. Right? If I define this to be gamma, then I get delta t prime times gamma. I just made a definition, right? I just said this and this are the same thing. It's just I defined it that way. I could call this whatever letter I want if I want to. You can call it X. You can call this thing X, but then this would have X there. Okay? I'm just using a definition. Gamma is not something special other than it's defined as this thing. It's just a defined thing. It's not something that comes from theory. It's just it's a defined value. Okay?
Yeah, I got it. Thank you.
Okay. Okay, so the observer in the frame that is moving is moving relative to the two events, says that the clock, yeah, I said that, I got to fix that sentence. But the observer is saying that the clock in the moving frame runs slow. I got to fix that sentence. That sounds bad. And then the observer in the frame that is at rest, relative to the two events, measures the events at the same location in space. So the person on the rocket measured the location, the two events at the same location. The observer did not. The observer actually needs two synchronized clocks at two different locations to make the measurements. The time that the person in the rocket measured is called proper time because the two events happen in the same space. Same place. Okay? This time over here is called proper time because the two events were measured in the same location according to that person. According to us, who are watching the rocket go by, they were not measured at the same place. So we don't call that proper time. That's a definition. It's just a definition. By the way, what time is it? Okay. So let's take a break. Let's get back at 12, what time is it now? 12:50. Okay? Eat something. Take a break, because I can't talk for 3 hours straight, and I'm sure you can't listen for 3 hours straight. And so what I do in my lectures, I make videos of my lectures. I ask to break them up into two parts because I'm using a Mac, and the Mac makes these big MOV files that are like 12, 13 gigabytes, and it takes forever to upload them onto Google. Okay, so I'm going to